Let's get started. Markov models. That's the topic for today. It's one of the very complicated topic in terms of what happens, from a stochastic theory point of view. It's usually about a semester long course in math departments on stochastic theory. Um, and Markov models are essentially stochastic models. Okay, so but then this topic for today I have made in such a way that it's much more accessible, and we are going to talk only from an kind of a very schematic point of view rather than going through any of the theories. I mean, there will be some equation towards the ends, but I have kept this to a very basic idea. Okay, most of these topics that you need to practice at in your home, or try to get some problems and try to solve it, uh, either using some of these already built-in routines, right? Or if you're interested in more theoretical aspect of it, you can work through some of the classic textbooks, the Springer books, series in mathematics. Okay, but the idea is to understand how Markov models are essentially applied across almost all fields that we can imagine, from finance to biology, to economics. It has a vast applications. Okay, so the reason that will be apparent in some time why Markov process is such a powerful process, right? So we will first go over a Markov process. What does it mean? And then we will see some examples of a hidden Markov model. Okay, why is it called hidden? And there are classic algorithms for finding some of the probabilities. There are three essential problems when it comes to Markov models. One is the uh, one is the evaluation problem, the other is a decoding problem, and the learning problem. So we will see that how the evaluation problem is solved by forward algorithm, and then we will see the decoding algorithm is essentially Viterbi's algorithm for solving the states. And I will not go over the learning problem, which is much more harder and complicated. That's I would suggest doing that probably later when you are familiar with the Markov ideas, because that assumes some of the probabilistic models such as expectation maximization, etc., etc. So we will not cover the learning model today, but essentially we will be going over a couple of algorithms, and then we will see a tutorial on how this is applied for a practical case of how we identify some of these states in DNA when it comes to the biology. Okay, so we are primarily interested in finding patterns that appear over time. Okay, so we are interested in a sequence of events, and such process appear in many areas in nature, right? Consider biological sequences, DNA, RNA, proteins, and these are all these DNA sequence, right? And also sequence of words when it comes to natural processing. And weather phenomena, right? We have an event. It could be a rainy day today. Tomorrow it could be cloudy. So we have some sequence of discrete events, and there are continuous Markov processes which we will not go over, but we are primarily interested in some discrete events, at least for the scope of this lecture. Okay, so we are interested in knowing if the sequence makes some useful patterns which can be modeled. So that's the fundamental idea behind the Markov process. So for instance, a simple example, sequence of traffic lights. You have red. If you're in Europe, it's red and amber, and then it comes to green, and then it once again comes to amber, and then red. Okay, so this can be viewed as a trellis diagram. So this is a classic diagram. The state diagram is called the trellis diagram. Okay, so you have a stop, and then you have kind of a red amber here, and then you have a go, and then you have to prepare to stop, and then it feeds itself, right? So the key characteristic of this state is that each state is dependent solely on the previous state. It's a deterministic system. and it is what is known as an observable Markov process. Okay, so the key characteristic of a Markov process is that each state, let's say that each of these are called states, right? They are dependent only on the previous state. The go does not depend on the red, it only depends on red amber, right? So this is a classic example of a Markov process, that every state should be dependent on the previous state. Okay, so as an example, deducing a weather from a piece of seaweed. Okay, weather is a classic example of a Markov process. So if you think about how today's weather could be influenced by yesterday's weather and probably a couple of days back, right? I mean, it doesn't go back to really long. So it's like kind of a memory-less system, right? So that's a classic hallmark of a Markov model. So deducing weather from a piece of seaweed, right? So if it is soggy, we can kind of say, then we can say that it may not be sunny, right? If it is damp, it means that we can't be sure. So the state of weather is not dependent on the state of seaweed, right? So although it is not, the state of weather is not dependent, right? But we can say something like it is raining if the seaweed is damp, right? So another clue could be the state in the preceding day, right? With a combination of this knowledge, we would be able to come to a better forecast, right? So these are the classic examples. Now, consider systems which generate probabilistic events, right? From weather fluctuating between sunny, rainy, or signal going from amber to red. Now we can look at the system and we wish to predict uh, what we wish to predict is not what we observe, right? So there could be the weather could be a hidden system, but the what we observe is whether the seaweed is damp or soggy, right? This is an observe. What you observe is different from what is actually the state, right? So this is an example of a hidden system, right? In the seaweed example, the hidden system would be the actual weather. And for instance, in the traffic light example, the hidden system could be the actual signal, while the observed sequence would be some traffic movement, right? We don't need to really see the actual signal, but looking at the car stopping, right? Those are the observed variables. We would be able to infer something. So some problems can be solved once the system is modeled, and the idea, that the memory less is actually helpful in modeling such processes. So, so we can also see that what the weather was for a week given each day's seaweeds observation, right? So given a sequence of seaweeds observation, is it winter or summer, right? I mean, we can see that intuitively if the seaweed has been dry for a while, we can say that it's summer or it is winter, right? So for each of these, right, we typically build a trellis diagram. So where each state depends only on the previous state. So for instance, in this weather example, each sequence taking a single day, right, with self-transition. And one possible sequence would be, there would be a sunny day, and then the next day could be a cloudy day, and then the day after that could be a rainy day, right? Or the sunny day could be could be followed by a sunny day. Okay, so that's what this transition means, right? So if we look at all possible sequences, there could be a sunny day, and then there could be a cloudy day, and again it can get back to sunny. So these are all possible sequences for a Markov process. So there could be all these transitions could take place, right? And now we can embed probabilities within the sequence. So we can say that, for instance, a sunny day could be followed by a cloudy day with a probability of 0.2, right? Or a cloudy day could be followed by a rainy day with a probability of 0.3, right? So we can embed all these probabilities, and note that the probabilities should sum to 1, because a day should be either sunny or cloudy or rainy, right? So the probabilities should add to 1, and then you can embed the sequences with probabilities. So usually these probabilities, right, they are converted into what is known as a transition matrix. Okay, so this diagram, right, whatever that state diagram, could be just represented as a matrix. So sunny, cloudy, and rainy, right? These are the rows, and then the columns could be again sunny, cloudy, and rainy. And you can say that the probability of going from sunny to sunny is 0.5, sunny to cloudy is 0.2. So you can represent the entire state diagram into what is known as a transition matrix. Okay, so this is called as a transition matrix. In many cases, the patterns are not apparent. Okay, so for instance, a crab may have access only to the seaweed and not to the weather, right? So it may just look at the seaweed and kind of infer what it could be the weather, right? So we have two states essentially. One is an observable state, in this case, seaweed, and the hidden states could be the state of the weather, whether it's sunny, rainy, or cloudy, right? Now, we have to devise an algorithm for, let's say that there is a crab, it has to forecast weather from the seaweed and the Markov assumption without actually ever seeing the weather. So that's the problem. You have some set of hidden states and you have observing some other uh, observables out of those states. Okay. Now, could you infer the states through observable? That's the whole idea behind the Markov process, right? But note that the number of hidden state may be different from the number of observable states. Okay, so there are two things here. The observable states could be dry, damp, and soggy. Okay, whereas the weather states could be sunny, cloudy, humid, and rainy. Right? I mean, there could be several states, and the observable state may be different from the actual hidden state. Okay, so those are the key thing about hidden Markov models is that you have two set of nodes or states. One is an observable set of states, and the other is a hidden state, right? So, for instance, in this case, right, you can have all these transitions. We already have these transitions from sunny to cloudy to rainy, right? And then you can have a set of observables. Say state could be soggy, damp, dryish, or dry. Now, there is a matrix that could give rise from sunny. You can infer if it is soggy, it could have some probability of being sunny. If it is soggy, there could be some probability of being cloudy, or there could be some probability of being rainy. Okay, so you can have all these arrows that represents the probabilities. Okay, that probability has a special name. Okay, this is called emission probability. Okay, so there are two things. One is a transition probability that that happens from nodes to nodes, and also there is an emission probability that you have from hidden states to the observable states. Okay, so the hidden states are modeled by a simple first order Markov process, and the connections between the hidden state and observable state represent the probability. Okay, so all these are all probability. We have to think of it as a probability, and the probabilities entering an observable state will sum up to 1, right? Or because it could be if you are either having an observation, it could be sunny or cloudy, or there will be a probability of rain. So the total of these things should sum up to 1. Okay, so that's the key constraints for the Markov models. So apart from the transition matrix, we also have an emission matrix, right? I was telling you that there is also an emission, that you have observable states, right? And these observable states, right, they underlying the observable state is a hidden state, and the one of the key characteristics of a Markov model is that they are time independent, in the sense that you have an observable emission matrix and the transition matrix. They are fixed in time. Okay, so they don't really move around. Okay, so that's the most unrealistic assumptions of Markov models when it applied to the real process. Okay, so in reality it could be different, but an underlying assumption is that when you have some states, it is all fixed. Okay, so that's the hallmark of the Markov model, is that it doesn't vary or change in time. Okay, the matrices, right, the probabilities just remain fixed. So there are three main problems that you can solve using this hidden Markov model. One is an evaluation problem. Okay, and it's a kind of pattern recognition. the idea is to find the probability of an observed sequence given a hidden Markov model. So if you're seeing a day is, if you're watching the seaweed and it is dry, okay, so what is the most probable state underlying the fact that it is if it is damp. Let's say that you are seeing a seaweed and it is damp. So the days could be either sunny, cloudy, or rainy. But what is the most probable state that when you have what is the probability of this sequence given a hidden Markov model? Like if you are observing a seaweed state is damp, what is the probability of having such an observed sequence, right? And there is another problem which is called as a decoding problem, which is also kind of a pattern recognition problem. It is actually the problem of finding the states given some observations. Okay, so you are observing a seaweed which is damp, and now you are trying to infer what is a possible weather behind that state, behind that observation, not state, behind that observation. Okay, so that's the classic um, um, problem when you have to find the hidden state just using the observations. Okay, and there is another set of problems which are learning problems. So you have to generate a hidden Markov model given a sequence of observations, which means that you have to find the parameters of the probability distribution that underlies the hidden Markov model. Okay, so the evaluation problem is number of you will have several number of hidden Markov model describing different systems, and you have to come up with a sequence. You have a sequence of observation. Which hidden Markov model is probably generated the given sequence? Okay, so for instance, you can have a summer model and you can have a winter model, and then you can determine whether the summer model is better or the winter model is better for the sequence of observations, right? So usually it is carried out by what is known as a forward algorithm to calculate the probability of an observation. Okay, so you usually what is this been done by a forwarding algorithm. We will see the forward algorithm. And the second problem that could be solved by hidden Markov model is decoding. So you find the most probable sequence of hidden states given some observation. Now, for several times, you may want to see what are all the hidden state. Like for instance, CPG islands, right? You have a genome, and there could be lots of CPG islands in the genome, right? Especially when you have near the promoter, it's going to repress the gene expression, right? So, with using just the sequence, can you identify the hidden state of where the CPG islands are, or even there is a chromatin state, right? When it comes to epigenetics, you have all these marks, right? Chromatin, the histone marks. Some of them are activating, some of them are repressing. So, is there a different marks that you can identify using this observed state? That's a classic application of hidden Markov model, and there is a program also called Chrome HMM, right? So that's using the hidden Markov model to identify these marks, these chromatin marks, right? So in our own example, identifying the weather, only knowing the status of the seaweed, will we be able to identify the weather? And for this, there is something called Viterbi's algorithm. It's a very beautiful algorithm. We will see how it works, and that's those are the two important algorithms. Okay, and then there is a big set of problems of learning. This involves generating a hidden Markov model from a sequence of observations. So we take a sequence of observation from a known set, right, training set, and then to represent the set of hidden state and fit the most probable hidden Markov model. And there are lots of algorithms. Usually it's done by expectation maximization, um, but it's more complicated problem. We will not go over that in detail, or probably even not. But the most important things to for you to focus on would probably be the forwarding algorithm, and also the Viterbi's algorithm. Okay, so this is an example of a forwarding algorithm. Okay, you have states here. Let's say that there is a dog, and it is sometimes hungry, happy, or sleepy. Okay, so these are the hidden states. And there is a transition. The dog can go from being hungry state to a happy state with a probability of 0.3, from happy state to hungry state with a probability of 0.4, and also from hungry to sleepy with these probabilities, happy to sleepy, and it can keep on going from hungry to the hungry state. Okay. Now, what you observe, let's say that the dog could be restless, or it could growl, or it wags tail. Okay. So if it is hungry, most of the time it is either restless or growls, right? If it is happy, then probably it wags tail most of the time. And if it is sleepy, it is restless most of the time, right? Or sleepy or either growls, right? So the dog's behavior depends on its state. Okay is the observed state, right, at a time t, and depends on the previous time at state t minus 1. Okay, so that's a classic representation. Okay, yeah. Percentage. Oh, okay. So this is which one? Which one doesn't add up to one? Yeah, it is probability. Yeah, it is not percentage. It is a probable. Yeah, it's a probability. So if a dog, so predicting the state after n observations. Let's say that if I observe the dog wagging its tail at time t, and I know the dog was hungry at time t minus 1, what state the dog is in? So I'm asking this question. So this can be modeled. So observed at time t, right, is wagging tail, and we know that at t minus 1th state it was hungry, and you need to know what state at time t is in, right? So this is a classic Bayesian problem. How many of you know Bayes formula here? Probability of A given B. Okay, so that's something basics that you may want to see. The probability of wagging tail given that at time xt, okay, um, and also we know that it is hungry at time step t minus 1, can be written as this probability, right? It is the same as the observed is wagging tail at given xt, at t minus 1 it is hungry, and we can write using the Bayes formula that this probability is nothing but probability at time xt given xt minus 1 times the probability of observed is equal to wagging tail given what is the state at xt, right? So what is this? This is the classic transition probability, and this is the emission probability, right? So you can easily compute that. So for instance, each of these, right, what is the probability of xt given xt minus 1? You know these probabilities, 0.5, and then you can compute it with the emission probabilities observed by xt minus 1. Okay, it's a simple multiplication that you can find out, and then we can maximize and see that which is the most probable state it is in, right? So let's say that we know how to compute the probability of the current observation given the previous and the current state. Okay, so, but to do this, after n observations, I need the probabilities of my starting state, right? So for that, actually, you may have to have some prior knowledge. Okay, so this is where the prior comes in, and you can say some experience that dogs are hungry 30% of the time, happy 40%, and then sleepy 30% of the time. These initial probabilities can also be simulated. You can try to fit in several of these initial values and then see how it performs. So this, once you have this, we can see that the conditioning, right, probability of A is over all B, the probability of A given B times probability of B. So the probability of my model producing a set of observations is probability of O, probability of the observation. You can sum up all the possible combination of the states. Okay, so the probability of observing, let's say that some of these, one of the state would be sleepy, hungry, or what's that, the third one is what, happy, right? So these are the three states, and you can take the combination of all the three states, right? So it could be sleepy, sleepy, happy, and hungry, hungry, sleepy, happy, and you can take all the combinations, okay? And so the probability of observing an event is given by the summation of all that, right? So, and we know that the probability of this is nothing but the transition probabilities, right? Xt given xt minus 1, because the state xt depends only on xt minus 1, and also the probability of observed is the emission probabilities. Okay, therefore you can write this probability of x o is a summation for the and then you take the product of all the possible all the probabilities. So this is a huge computation. Okay, so if there are n states and t time steps, it is n power t times t. This is a huge computation. Okay, so that is why we need an algorithm to do that. And the key observation comes from the fact that a state at time t can only be dependent on state t minus 1. So you really don't need the rest of the combinations if you think from a more heuristic point of view. Okay, so that is what the forwarding algorithm does. So what it does is, let's say that alpha I of t is the probability of state xi at a time slice t with a history of observation. Okay, so alpha I is nothing but the probability of being in a state xi at time t. Okay, now what you can do is that you can write this, right, xt I and xt minus 1, because the xt depends on xt minus 1, right? And then there's a simple chain rule, which is a very important rule in probability. So this probability of xt minus 1 can be written as probability of ot given xt minus 1 times probability of xt given xt minus 1 times probability of xt minus 1 with the observation. Okay, so you can write it as a chain rule. And once you get this, it's pretty easy. What is this? This is nothing but the probability of OT given XT, because some of these it does not depend on, we are only interested in the observation at T, right? And also this is the state T and T minus 1. And this is alpha J of T minus 1. And so you can compute this quantity, you can take this outside and then compute this quantity. So this reduces tons of calculations. The computation time is n squared t and can be represented in a trellis diagram. So what it does is it goes from state to state and then it tries to identify the maximum. Okay, so for instance, suppose I observe the dog during the 3 hours. Okay, in hour 1 it wags tail, in the hour 2 it's restless, and in the hour 3 it's wags tails again. So what is the most likely state the dog can be in? So let's take only 2 time slices, right? And we can compute this quantity, alpha of sleepy at time 0, alpha of happy at time 0, and alpha of hungry, right? And you have these 9 states here. And we know if it at t equals 1, if it wags tails, what is the probability of being in other sleepy state, right? So we can compute this quantity just like this, right? We have this formula, right? Alpha I. So we can compute this formula and then see which one is the maximum and then identify the state, okay? So the same idea here. At time 2, if you know that it is sleepy and happy and hungry, we can compute the alphas and then see which one is maximized, okay? So this is the forward algorithm. So you go from state time steps to time steps to time step. Okay, so you really don't have to be worrying about all of the states at one time. Okay, so the goal is, given some observation, what is the most likely. So this is the forwarding algorithm, and you can see what if you are given a bunch of observation, what state you are likely in. Okay. Now the decoding problem is a little bit harder than that, but the idea is the same. So the goal is, if you are given some observation, you have restless, wagging tail, and growl. What are all the most likely sequence of states that leads to these observations? Okay, so that's the key idea here. But the same idea applies here. You take a state, you know that out of these, at every state, you can maximize the probability, right? And that's the key idea behind the Viterbi's. It's similar to the forwarding algorithm. So what you do is that at every time step, you see what is what maximizes the probability. So there is a very nice tutorial I was actually thinking of making this, but I saw that there is a very nice tutorial for Viterbe's algorithm, and I thought I could just play it instead of.
Hello, my name
Oops.
is Jug, and I'm going to.
Is there a way that I could? Let's see. I think I need to install this. Oops. So this is. Okay, I think it should work. Is it connected already? All right. I hope this will work. Let's see.
Summary. So I'm going to do this with an example of trying a road trip from the west coast of the United States to the east coast. And the way I've done this is I've considered 4 possible cities as we started with on the west coast: Seattle, Newport, and San Francisco, which I've labeled USD. And I only want to drive less than 750 miles a day each day. So, for example, I'd say the first day that I use the 4 possible cities: Boise, Salt Lake, Las Vegas, Tucson. And then the third day, it's the pink-colored cities of Casper, Denver, Albuquerque, El Paso, etc. And so this would take me 7 days, and each day I would drive less than 750 miles. And the problem I want to consider is what's the shortest way to go from the west coast to the east coast? So I know it's going to take 7 days, but I want to drive the least amount of mileage. Okay? Let me get rid of the background, and then you can see this diagram a little more clearly. So this diagram is called a trellis diagram in the context of Viterbi decoding. And it's basically a diagram that shows all the possible routes you can take from the west coast to the east coast under this 750 miles a day or less constraint. So one way you could solve this problem of finding out what the shortest path is just to make a long list of all the possible routes that you could take and take the sum of their 1 day mileage to get their total mileage for each of the routes. Now this is there are a lot of these paths, so that's really what the problem is. So for example, if you consider just that you're in Salt Lake, there's 3 ways to leave Salt Lake. One is Casper, the other is Denver, the other is Albuquerque. There's 3 ways to leave Casper, there's 3 ways to leave Denver, there's 2 ways to leave Albuquerque. So if you just look at after 2 days of traveling, leaving Salt Lake, you're up to 3 plus 3 plus 2, or 8 different routes just in those 2 days. And then if you consider extensions of those routes from the ones from Pierre, Lincoln, Amarillo, etc., the number of possibilities keeps to grow very rapidly. So it's really not practical to write down a list of all the possible routes. There's got to be a better way. And in fact, there is a better way to do this. And that's exactly what the Viterbi algorithm does. So I want to try to explain the core ideas of the Viterbi algorithm and the execution of the algorithm. using this toy example. So the way to think about it is to first sort of condition on one potential city. So let's focus on Boise. Now, what I want to illustrate is if I say, if I just hypothesize that the best way to go from the West Coast to the East Coast uh, goes through Boise, then I can kind of break this shortest path problem into two segments, namely a segment to the left of Boise and a segment to the right of Boise. And to illustrate this, I'm going to provide a little bit of side information here that I happen to know. I happen to know that the shortest path from Boise to the East Coast is colored in here, the one colored in here by this green crayon. So it goes Casper, Lincoln, Kansas City, St. Louis, Pittsburgh, Washington, and that's 2,685 miles total from Boise to Washington now. Okay? So the idea here is that regardless of how I arrive at Boise from the West Coast, whether I came from Seattle, Newport, or San Francisco, the best way to go from Boise to the East Coast is still this green crayon line, and it's still 2,685 miles. Okay? So now you can very, very quickly reason that you really don't need to consider Newport, San Francisco legs to Boise, because Seattle to Boise is shorter. In other words, if you were to claim that the shortest path to go from the West Coast to the East Coast, passing through Boise, started in San Francisco, I could counter that argument by saying, well, let's start in Seattle and go to Boise, and then we both follow the green crayon path from that point forward. And clearly, mine will be less, the path from Seattle will be less than the path from San Francisco, because it's 494 miles from Seattle to Boise, and it's 648 if you start in San Francisco and go to Boise. So this allows us to eliminate the paths that go from Newport to Boise and San Francisco to Boise, and just keep the shortest path from the West Coast to Boise, which is Seattle. So by considering conditioning on the state of being in Boise, we decouple the problems into two shortest path problems. One is still hard, that's the green crayon one that I gave you the answer to. The other one is very easy, it's just the shortest way to go from the West Coast to Boise, and that's a very simple calculation. We can all tell that's Seattle. So we repeat this step at Salt Lake, Las Vegas, and Tucson. So Salt Lake only has one, Tucson only has one way to get there from the West Coast. And Las Vegas would just be a simple comparison between the way to get there from USC and the way to get there from San Francisco. And of course, USC is going to win out because it's 275 miles. So after one step of the Viterbi algorithm, this is the status. We know the shortest path from the West Coast to each of the day one destination cities. And we've also kept track of what those best paths are. Those are the lines with the arrows. And the mileage of those best paths at each of the cities. Those are the yellow numbers near the cities. Now let's repeat this over and over, and that's the Viterbi algorithm. So now let's first go and condition on Casper at the end of day two. Okay? So we need to find the best path from the West Coast to Casper. And we can tell that that has to be the one coming from Boise or Salt Lake. And there's only two of those because we've eliminated the other paths coming from, for example, Newport, San Francisco, going from Boise. We already got rid of those. So we really only need to consider the two paths, which are the extensions of the arrowed paths. And we add on the one-day mileage for each of those. So for example, if it came from Boise, it would be 494 plus 669. If it came from Salt Lake, it would be 748 plus 402. So we need to compare those two sums and choose the shorter, the smaller of those two. And it turns out that 748 plus 402 is smaller than 494 plus 669. So Boise is going to lose out. Okay. So now the shortest path from the West Coast to the East Coast, the shortest path from the West Coast to Casper is San Francisco, Salt Lake, Casper, and that's 1150 miles. Okay. And now we'll repeat this at Denver, Albuquerque, and El Paso. Denver is, again, not very interesting. There's only one way. In Albuquerque, though, we have three numbers to compare. 748 plus 609, that's if you came from Salt Lake. 275 plus 576, that's if you came from Vegas. And 528 plus 452, that's if you came through Tucson, Arizona. Okay? So if we do those comparisons, and then we select the shortest path up to that point, we arrive at this state. So this process of adding the shortest path up to a particular state with the one-day path, and then comparing all happened at a given destination day city is called an add, compare, select. So we eliminate the losers, we keep the winners, and the winning paths, the paths that are labeled there with the arrows, those are known as survivor paths because they survived the ACS elimination. And you can already see that the best path on the west coast to the east coast doesn't go through Boise. So even though we had hypothesized that in order to do some early elimination, it turned out not to be true. Okay. Notice also that even though I gave the green crayon answer for Boise, we really didn't need to know exactly what that answer was in order to eliminate Newport and San Francisco. Okay? We just know that that path has to exist. We don't know what it is, but the fact that we know that it has to exist and it won't change by how we get to Boise allows us to do some early elimination, and that's the key idea of turbography. So now we would repeat this again for the destinations, day 3 destination cities. For example, start in Pierre and compare how you could get there from either Denver or Casper to the add, compare, select, and repeat it at Lincoln, Amarillo, and San Antonio. And then we would move on to Minneapolis, Kansas City, Fort Smith, Houston, etc., all the way across the country. So if you do that, this is the result. And at the end of this 7 days of travel, potentially, or planning these 7 days of travel, you would see that we'd have 4 survivors at the East Coast, 1 at MIT or Boston, 1 in Washington, 1 in Wilmington, 1 in Daytona Beach. And if you compare the total mileage associated with each of those cities and those survivor paths, those are the shortest ways to go from the West Coast to each of those cities. And so clearly the shortest path from the West Coast to any city on the East Coast goes from, or terminates in Daytona Beach. So the last step of the Viterbi algorithm is to look at the survivor on the East Coast that has the smallest distance or metric. So in this case, it's Daytona Beach, and the metric is 2658. And the last step is what's called a traceback or traceback and decode operation. And so you want to know the shortest path or the specific legs of the path. You just look backwards. So you start at Daytona Beach, you look back and you say, well, we came from Tallahassee. You look back from Tallahassee, well, we came from New Orleans. You look back, we came from Houston, etc. And you find out that you started at USC. So now we know that the shortest path, in fact, travels from USC to Daytona Beach. Okay? So this algorithm was first introduced to the community by Dr. Andrew Viterbi, our own Andrew Viterbi, first published in 1968. This has been a revolutionary algorithm in the field of digital communications. It's ubiquitous in digital communication modems. And so it's really just based on these very simple ideas of eliminating options as early as possible using this principle of dynamic programming. And then another key innovation which is critical and is unique to the Viterbi algorithm, was critical for the early development and deployment of the technology, is this method of storing the winners as you go, so that in order to figure out the best path, you just do this traceback and decode. That's a very unique property of the Viterbi algorithm.
All right. So that's the idea, right? I mean, this is called a classic dynamic programming in algorithm. When you have an optimal substructure, when you have a structure and you have an optimal subproblem, you can solve those subproblems, and then solve the whole problem by dynamically looping through. So this is there is a nice this is a book. If you go to my algorithms course, you will see that there is a nice book. It's a classic book in algorithms. They have dealt with these kinds of things in detail. Okay, so let's move on, and that's the idea behind um, Viterbi's algorithm. Now, this is a tutorial on hidden Markov and Markov models using DNA using a DNA sequence. So the idea is, first of all, when you have we can have a multinomial model of a DNA sequence, right? So it's the simplest model, right? It can produced by the random process and randomly choose the 4 nucleotides in some probability distribution. You can call it as PA, probability of C, probability of G, and probability of T. and we can assign some probability of A equals 0.2, C is 0.3, etc., etc., and then you can generate a sequence. And this is a okay model. I mean, for most of the genomes, I think it should be okay. But the problem is that it assumes the frequency of all nucleotides is same throughout the genome, right? Which may not be the case. So there are, for instance, CPG islands, etc., etc., where one nucleotide is dependent on the previous nucleotide, right? So this model may not really work well when we consider the genome in general, because there are all lots of these areas where it is dependent. One nucleotide is dependent on the previous nucleotide, right? The Markov sequence is a better model, because there you can take the context, right? I mean, you can take the previous nucleotide, and then and then we can try to define a transition matrix. So, for instance, you have the nucleotides A, C, T, and G, and after A, you can have the probability of appearing the if the previous nucleotide was A, you can have the probabilities, and after that, if you have the previous nucleotide was C, you can have the probabilities like this, and then you can construct a transition matrix. So what it means is that if A precedes A with a 0.2 probability, A precedes C with a probability of 0.3, etc., etc., right? And using this, you can generate the DNA sequence. So what you need to do is that we have to just have the first initial probabilities, which could be any of these four with the equal probability distribution, and then you can actually generate looking through what was the previous position, and then you try to generate the next one, right? We're using this transition matrix. This is fine. I mean, this is usually uh, the Markov model, right? But sometimes what might happen is that you might have states in the genome, for instance, the GC rich regions and AT rich regions, and these could be different, right? So a hidden Markov model, right? We could construct a hidden Markov model based on whether a sequence is GC rich or AT rich. You can generate such sequences, right? That will be a more realistic simulation of the DNA sequence, right? So, for instance, these we can call it as states, the GC rich and AT rich as states, and then you can assign the probability of switching states, right? These are the transition probabilities of zero point 0.7 and zero point 0.3. So, if it is an AT rich region, the probability of switching again to AT rich region is zero point 0.7. Okay. If it is GC rich region, the probability of transitioning into AT rich region is 0.1. It's very low, right? And the second important thing that we need is an emission matrix, right? For emission matrix is observations. So you are observing, all you are observing is the four nucleotides, right? So we can assign probabilities for these four nucleotides on each of these states, right? So for instance, the AT rich probabilities for these two could be this 0.39, 0.1, etc., etc. And then the probability for GC rich could be these four probabilities, right? Now you can have an emission matrix. The emission matrix is A, C, G, and T, and AT rich, the probability of observing A in the AT rich region is 0.39 and T is 0.41. The rest would be smaller. And similarly for GT rich region, you can construct these emission probabilities. Once you have these emission and transition probabilities, you can generate the DNA sequence, right? I mean, you can generate the sequence by taking these probabilities into consideration, and then you can make the sequence. So you define the initial probabilities for the states as 0.5 and 0.5, and then you can generate this. So for the position 1, it generated T, etc., etc. You can make this. Now, the same thing, right? This is actually for simulation. If you want to simulate a genome, if you want to, make your own genome and then compare with the existing thing, you can do that. Now, what about if they are already given a genome and you want to identify AT and GC rich region, right? That's where we do do the Viterbi algorithm, right? We take the Viterbi's, and this is given in this applied statistics for bioinformatics using R, and it is just a standard implementation of that. Now, once you have once you implemented it, then it's easy. You are given a sequence. What you need to do is that you can just call this algorithm with the sequence, and it is going to tell you the possible state whether it is AT rich or GC rich. Okay. Now this has been applied. This kind of a model can be applied for, say, chromatin states. right? The hidden Markov model to identify that whether your histone is, histone acetylation, etc. What marker it is, it's a repressor or an activator mark and things like that. We can just use the same algorithm, the same idea to work on identifying these states, the hidden states, which we really don't know, right? So that's where the hidden Markov models are extremely powerful, because most of the time we will be only seeing the observations. We will not be knowing this what exact states that constitutes those observations, and this can be a powerful tool for doing identifying that. All right, so I think I would just stop with this for today, but I would suggest you to go